We are absolutely surrounded by computers, but let's be honest, how do they really work? Today on The Explainer, we're going to peel back all those layers of abstraction. We're taking a journey from a single line of your code all the way down to the actual flow of electricity that makes it run. You sit down, you write some code, maybe it's Python, maybe C, and it just works. It feels like magic, right? You type some text, and this machine does something incredible. But how? How does a physical box of silicon and metal actually understand an abstract idea? Well, that's the big mystery we're going to solve today. In computer science, we have a way to manage all this craziness, and it's this idea that's sometimes called turtles all the way down. Basically, we build one layer of abstraction, kind of hide how messy it is, and then we build another, simpler layer right on top of it. This entire explainer is just us unpacking those layers, one turtle at a time. So we're going to tackle this like we're taking a bite out of a sandwich, from two sides at once. First up is the top-down bite. We're starting in the world we all know, the world of software, and we're going to follow an idea as it gets translated into something the hardware can actually work with. See, our idea has to travel through a bunch of layers. It starts out in a high-level language, something like C, which is pretty easy for us humans to read. Then, a program called a compiler comes along and translates that into assembly language, which is a lot closer to the metal. From there, another tool, an assembler, turns that into the only thing the hardware truly gets, machine language, just pure ones and zeros. To make this all feel real, we're going to follow a single, simple instruction from a really cool modern architecture called RISC-V. The command is add S6, S3, S4. And all this means is, hey computer, take the number you have stored in a little spot called register S3, add it to the number in register S4, and then please stick the result in a register called S6. Simple enough, right? So, how in the world does add S6, S3, S4 become a string of ones and zeros? Well, it's not just a simple translation. It's more like an encoding process. Every single part of that instruction gets converted into a very specific pattern of bits, all following a super strict blueprint. And this is that blueprint. For our add command in RISC-V, it's called the R-type format. Just think of it like a form you have to fill out. The opcode field, that tells the processor what kind of instruction this is. RS1 and RS2 are where you name your source registers. RD is the destination for the answer. And those funct fields get into the nitty-gritty, specifying that we mean add and not, say, subtract. So, once the assembler fills in that blueprint with all the right binary codes for add and our specific registers, what you get is a single 32-bit number, a long string of ones and zeros. And that's it. That's the command. To the hardware, our entire beautiful program is just a long sequence of these numbers. Okay, let's hit pause right there. It's time to take a bite from the other side of our sandwich. We're going to start at the absolute bottom. We're talking physics here, and build our way up to a machine that can actually make sense of that 32-bit number we just created. The fundamental atom of all modern computing is the transistor. And really, it's just a microscopic switch. It's so simple. When current flows through it, it's on. That's a 1. When it doesn't, it's off. That's a 0. Every single thing your computer does, from loading a web page to running a game, is built on billions of these simple little switches. Okay, so how do we get from a simple switch to, logic? It's all in the wiring. If you put two switches, one after another, in a series, current is only going to flow if switch A and switch B are both on. Boom, that's an AND gate. Now, wire them up in parallel, and current will flow if switch A or switch B is on, and that's an OR gate. It's kind of wild, but with just these basic building blocks, we can construct the entire universe of computation. Now, by combining thousands of these logic gates in really clever ways, we can start building more complex components. And one of the first and most important is the arithmetic logic unit, or ALU. You can think of this as the mathematical heart of the entire processor. The ALU is basically a multifunction calculator. It can add, it can subtract, it can do and, or, and a bunch of other stuff. So how does it know which job to do at any given moment? Well, we send it a few bits as a control signal. For instance, if we send it the binary code 0010, all its internal logic gates configure themselves to perform addition. And this is it. This is the payoff. This is the moment where our two bites of the sandwich finally meet in the middle. We have our 32-bit instruction from the world of software, and we have our physical hardware built from transistors. So let's see what happens when these two finally come together. Every single instruction goes through a kind of assembly line inside the processor, which we usually call a pipeline. For our simple RISC-V instruction, it's a 5-step process: fetch, decode, execute, memory access, and finally, write back. Let's walk through it. First up, fetch. There's a special little register called the program counter, and its only job is to remember the memory address of our instruction. The processor uses that address to go out and retrieve, or fetch, our 32-bit binary number from memory and pull it into the CPU. Next, decode. The processor's control unit takes a look at that 32-bit number and all its different fields. It sees the opcode, it sees the function bits, and it has an aha moment. It recognizes, okay, this is an addition. It then goes and finds registers S3 and S4 and gets their values ready to send over to the ALU. Execute. This is where the magic happens. The numbers from our registers flow into the ALU. That control unit sends the special add signal, that 0010 we saw earlier, and in an instant, millions of transistors flip. The logic gates do their work, and the sum is calculated. Right here, in this moment, our abstract command becomes a physical computation. It's awesome. So our little instruction doesn't need to access main memory, so we can just skip stage 4. That brings us to the final step: write back. The result that the ALU just calculated is sent over to our destination register, S6, and it overwrites whatever was in there before. And that's it. The instruction is complete, and the program counter gets ready to fetch the next one. So we've seen the whole journey now, from top to bottom and back again. But what is it that allows this incredibly complex dance to work? Not just on your computer, but on trillions of devices, built by thousands of different companies all over the planet. The answer is one of the most important ideas in all of computing: the Instruction Set Architecture, or ISA. The ISA is the official contract. It's the sacred rulebook that sits right between the hardware and the software. Compilers promise they will only generate binary code that follows these rules, and chip designers promise they will build hardware that can perfectly execute any command that follows those same rules. This one contract, this single beautiful layer of abstraction, is what makes the entire modern world possible. It's what allows a company to design some radical new hardware while still letting it run all the same software you already have. And as a developer, you don't need to know a single thing about the circuitry inside. So what are the big takeaways here? First, abstraction is the one tool we have to manage this mind-boggling complexity. Second, having a simple regular contract like the RISC-V ISA makes for much faster, more efficient hardware. And maybe most importantly, there's no magic inside a computer. It's just layers upon layers of brilliant engineering. And you know what? Understanding these layers really does make you a better programmer. So we did it. We went from a single idea all the way down to a single transistor and back up again. We've demystified how one computer works. But what happens when you have a data center with tens of thousands of them, all working together on the same problem in the cloud? Well, that sounds like a story for another explainer.